This is the fourth quarter review key. 1 and 2 are knowing the mass of an object and the gravitational field strength, calculating the weight. On the moon, 4 kilograms is 6.4 newtons. On Earth, that would be 40 newtons. 3, you need to do a force diagram for the object, and that will include gravity down 20 newtons and a 10 Newton force at a 30-degree angle is all you know. Calculate the components. There's the horizontal component of that tension. There's the vertical. Calculations are done right here. And since this object is not moving, the forces are balanced, so that means this force must equal that force horizontally. Those are the only two forces. And this 5 Newton force plus this force must balance out the 20 newtons. And so here's the calculation here to figure out that T2y is 15 newtons right there. Knowing this side of this triangle and this side of the triangle allows us to figure out delta right here. And T2, the tension force there, is just using the Pythagorean theorem calculated right there. 4 and 5, ball on a ramp. A force diagram is needed to figure out the net force on the ball. There's no friction, so this x component of the gravitational force, and it's the x component if we rotate the axes, which you're going to do if you have a ramp, and that's the only force on the x-axis, so that is the net force on the x-axis. So using Newton's second law, and the x-axis information gives the acceleration on the x-axis, and now using that with a kinematics equation, we can calculate how far it's going to go in 1 second. In 5 seconds, which is given as the time. Elevator problem, calculate the apparent weight. Apparent weight is the normal force. So there's just two forces operating. You can calculate the weight given the mass. And so if the acceleration is known, Newton's second law, sum of the forces equals ma, allows us to calculate that. That's 120. So that just means that the upward force must be 120 newtons more than the downward force, which is 600. So the answer is 720. Here is a net force equation which shows how that can be calculated. Number 7, object 5 kilograms being pulled on a level surface, 25 Newton force. Here's the force diagram, and we know that there's no acceleration vertically. Forces are balanced. And if that's the force to the right, friction to the left must be equal. So no calculation necessary. Friction is 25 newtons. Using the Fun equation, calculate for the coefficient of friction, which is mu. 25 newtons of friction, 50 newtons of normal force is 0.5 for mu. Number 9, lots going on here. This box is 2.5 kilograms, going to accelerate 2 meters per second squared. That's mass and acceleration. That should make you think of Newton's second law. And here we go. Using Newton's second law, we get a net force equal to 5 newtons. That's along that line of travel. That's the x-axis here. So that means the sum of the forces on the x-axis must be 5 newtons. We want to figure out what friction is. Here is a net force equation for the x-axis. It's the x component of gravity, which is right there, plus the friction force. Those are the forces on the x-axis. So if I solve that for friction, that's going to be the net force subtracting out the x component of the gravitational force. So 5 newtons net force subtracting out that x component of the gravitational force is minus 16.6 newtons. Question 10 is a motion problem. We know the acceleration is given. Initial velocity is set as to be rest. It's going to go 1 meter down the ramp. Asked to figure out time. Using the kinematic equations available, use this one to calculate the final velocity, which is 2 meters per second, and then use this equation here to calculate the time. And the answer is 1 second, is how long it would take to slide long it would take to slide 1 meter. 11 is an energy analysis. The spring has elastic potential energy. It becomes transferred into kinetic energy and get maximum velocity. So setting these equal to each other and putting in the appropriate equations for elastic and kinetic energy, there's the maximum velocity of 9.13 meters per second. Horizontal projectile problem. You should realize that for horizontal projectile, we know that about the vertical initial velocity, we know that about horizontal acceleration, that about vertical, and we know that whatever the initial velocity is horizontally, it will maintain that velocity the whole time. And this is the height of the launch. Calculate time, 0.57 seconds, and then knowing how long it's in the air, just use the constant velocity times the time to get the change in position horizontally. 14 and 15 are projectiles that go to the original launch height. First, what's needed is a velocity triangle to get the components, x component, y component, and velocity. They show up there. X component doesn't change horizontally. If it comes back to its launch level, the final velocity is just the negative of the initial. That's the constant downward acceleration. There's the 0 horizontal. And the change in position vertically is 0 because it comes back to its own level. So calculate time here and then calculate displacement there. Very last problem is, suppose the projectile goes past its level of launch and keeps going to 2 meters below. So the table now changes. The change in y position will be -2. The initial conditions are the same, and the velocity stays the same constantly. We do not know the final velocity when it's at that point. Vertically, we don't know the final velocity. We know the acceleration vertically and horizontally. This equation allows us to calculate that final velocity vertically. It's 8 meters per second, but it should be a minus, and that is possible from the square root here. It is a plus or a minus. For us, it'll be a minus because we know it's going downward. So now using this equation here to calculate time, there's our -8 final velocity and a 5 initial velocity divided by the 9.8 acceleration gives that amount of time in the air to get to that point, and then using that time with the constant velocity horizontally, we see the change in position horizontally is 11.5 meters.